Welcome to Lecture 7 of Module 7. This is on the isotropic simple harmonic oscillator. It is also our first central force problem that we're going to be solving with factorization. So let's start by reminding ourselves of what the isotropic simple harmonic oscillator is. We begin with a Hamiltonian for the 3D simple harmonic oscillator, but we work in the special case where the frequencies in each direction are the same. And if you look at this Hamiltonian, you see we have the kinetic energy term. That p squared term is a px squared plus a py squared plus a pz squared divided by 2m. And similarly, the potential energy term is a 1/2 m omega squared with an rx squared plus ry squared plus rz squared. When we're working in spherical coordinates, we often drop the vector sign, and you're going to see that that's going to be dropped fairly quickly in the different Hamiltonians that we're writing out. And we work with the radial component squared, and then we'll work with the radial momentum and the angular momentum using the separation of variables. Now, we already solved this problem in Module 6 using the Cartesian representation. And here we're going to be using factorization after we separate the variables. So we're going to be working in the radial and angular coordinates. And the strategy is the same as what we did before. We first have to factorize the original Hamiltonian. Then what we should do is construct the factorization chain. You're going to see we're going to handle that just a little bit differently in this example. And then we would use the translation operator to find the wave functions. We're going to be talking about the wave functions in the in-class work that we're going to be doing associated with this lecture. In the lecture, we're going to just be talking about the eigenfunctions. And we're actually going to modify step 2, and instead we're going to use intertwining because that's going to allow us to solve all problems for all angular momentum at the same time. And this is something that shortcuts the complications that we have in working with the factorization method, and you're going to find it's a really nice shortcut, but you have to just be aware that there's a couple of little tweaks with the way that things work when we do this shortcut, and you have to make sure that you're aware of that in order to understand properly how that works. I will be careful to point that out as we get to those places where you need to be careful about that. Now, we're going to be using separation of variables, and as you recall, that really requires us to separate that kinetic energy into the radial and angular degrees of freedom. So we rewrite the Hamiltonian in terms of the radial momentum, pr squared, and the angular momentum. And this is a decomposition that we did in earlier lectures, and the potential energy stays the same, of course. Now, when we think in terms of quantum numbers, the Hamiltonian, the total square of angular momentum, and the LZ, they all commute. And this occurs because, as we remember, the radial momentum really just depends on the radius, has nothing to do with the angles, so that commutes with the angular momentum. The radial position operator, that also has nothing to do with angles, so that commutes with all angular momentum. And of course, L squared and one of the components of angular momentum also commute. And it's tradition that we pick LZ. So H, L squared, and LZ all mutually commute. We call that a maximally commuting set. And it means that we can find simultaneous eigenstates of all three. So we're going to label our eigenstates, if you like, by energy, by the square of the eigenvalue of the square of angular momentum, which has eigenvalues h bar squared L times L plus 1. We typically pick L as the label for that. And for LZ, which has eigenvalues h bar m, and we typically pick m for that. As you recall, we've worked out the angular momentum eigenstates. They're this ket L comma m, which already are the simultaneous eigenstates under L squared and LZ. And then we have to have the radial component as well, which we're going to call psi sub r. And the full wave function is going to be a tensor product of these two wave functions. You can think of this as a separation into a radial dependence and an angular dependence, if you like. So after factorizing that tensor product, when we apply the Hamiltonian onto it, take a look at that Hamiltonian. You see I have a pr squared. You can think of that as pr squared tensor with the identity because it doesn't act at all on the angular part. The second term, the L squared over 2m r squared, that's a full tensor product operator. The L squared piece acts on the LM part of the tensor product, and the r squared piece acts on the psi r part. What we're going to do is we're going to let that L squared piece act on the LM part. Because it's an eigenstate of L squared, it just multiplies that state by a number, which is h bar squared times L plus 1. And then the third part is a tensor product of a operator that acts on the r part of the wave function tensored with the identity, because it acts like the identity on the angular part. And so we find that these HLs become angular radial momentum squared PR squared over 2m plus h bar squared L times L plus 1 over 2m r squared plus 1/2 m omega squared r squared. And that is an object that acts only on that radial wave function, the psi r ket. Okay? And we have an infinite number of different Hamiltonians, each labeled by L. Each Hamiltonian is different because the Hamiltonian itself is a function of the L. But notice this Hamiltonian does not depend at all on m. And that means that the energy is going to be independent of m, as we're going to remind you about just now. So this Hamiltonian operator for each sector only acts on the radial sector, and it defines what the energy eigenstate equation is via HL acting on, I'm now taking that radial vector psi r and I'm giving it labels n and l, so it's a psi n l, and it's an eigenstate eigenvalue relationship. So there's an eigenvector ENL that multiplies that when we have found the eigenstate. And so the idea is, let's find the eigenvectors and let's find the eigenvalues, these ENLs that are associated with those eigenvectors. And this label n allows us to distinguish between the different energy eigenstates that have the same angular momentum, total angular momentum L eigenvalues. And as I mentioned before, because this Hamiltonian is independent of m, the energies are also independent of m. So we have these separate angular momentum Hamiltonians that we have to solve for the eigenvalue equations for. Now look at that function. This is something that has a momentum squared over 2m. That's the same kind of kinetic energy as we've been working with before. Remember, the canonical commutation relation of a PR with an R looked just like the canonical commutation relation of a PX with an RX. So this is the kind of Hamiltonian that we've been factorizing already. Now, we've already even worked with factorizing this when we looked at the second factorization of the simple harmonic oscillator. So if we think in terms of strategy, we want to have a linear combination of 1 over r and r, because when I square that, I'll get a 1 over r squared. The cross terms will give me a constant, and then I'll get an r squared term. And that's all of the terms that we have. And then when I look at the commutator term, the commutator with 1 over r will give me a 1 over r squared term, and the commutator of the r will give me a constant. And so we should be able to make this work, just like we were able to make it work for the second factorization in the one-dimensional simple harmonic oscillator. Now, in this case, we do have to remember that our radial component only goes from 0 to infinity. There's no such thing as a negative radius, because the radius is the square root of rx squared plus ry squared plus rz squared. And remember as well that that means that we're going to have a superpotential that diverges at the origin. That's the way that we guarantee that the domain corresponds to running from 0 to infinity as opposed to from minus infinity to infinity. And of course, if I have a superpotential that has a 1 over r in it, that is going to diverge at the origin. So we're satisfying everything that we need to satisfy with such a factorization. So what that means is we're going to have as an ansatz that our lowering operator on AL is 1 over the square root of 2m PR minus I alpha L over r hat. I'm incorporating a number of those constants, the h bar k and so forth, into a alpha L minus an I beta L times r. So I'm absorbing a number of constants into those constants alpha L and beta L. And now all we have to do is we have to calculate AL dagger AL and ensure that we get HL plus a constant. So let's go ahead and do that. When we calculate AL dagger AL, this is the same kind of thing as we've been doing before. We have a 1 over 2m. The PR times PR term gives me a PR squared. The cross terms give me minus I PR, the the commutator of PR with alpha L over R hat plus beta R times R hat. And then we have the square of the superpotential term, and that's going to give me an alpha L over R hat plus beta L times R hat quantity squared. So now we have to go ahead and work out what each of those different terms are. The commutator of PR with 1 over R hat, that's going to give me an IH bar over R hat squared. The commutator of PR with an R hat, that's going to give me a minus IH bar. And that's it because it's equal to a constant. And of course, I can work out the square by just foiling out those two terms and calculating the square of those operators. So when we do that, we get a PR squared plus H bar alpha L over R hat squared minus H bar beta L plus, and these are now coming from the square terms, alpha L squared over R squared plus 2 alpha L beta L plus beta L squared R hat squared. All right, now we just need to collect our terms, and you can see that if I chose alpha L equals H bar L, or if I chose alpha L equals minus H bar L plus 1, we're going to get that term H bar squared L times L plus 1. There are two different choices because that's a quadratic in L. If you do not see that this works, that H bar alpha L plus alpha L squared, if I substitute in alpha L equals H bar L or alpha L equals minus H bar L plus 1, if you don't see that that works and both of those give me H bar squared L times L plus 1, then please pause the video, get out a piece of paper, and check and verify that that works. The terms with the beta L are much easier to sort out. We just need beta L squared to equal m squared omega squared for this to work. So we have beta L is equal to plus or minus m omega. And now we have 4 choices that we have to pick from. Of course, only one of them is the one that we want to pick for our factorization chain. How do we choose? Well, we have to remember what are the properties of the superpotential. One of our requirements is that the superpotential is positive as R goes to infinity. That means that I have to choose beta L equals m omega. Now, there's a similar requirement that we didn't list in our original list of rules, but as R goes to 0, the superpotential diverges, and the coefficient of that divergence must be negative in order for the wave function to be finite as R goes to 0. And so that's our second requirement. And that means we have to pick alpha L equals minus H bar times L plus 1 in order for the superpotential to be negative as R goes to 0. And with that, we've reduced our 4 choices just to 1. We only have 1 choice. That's the one we're going to pick. Okay, so when we plug that in, we now have to work out what those constants are. And we find we get a minus 1/2 H bar omega and a minus H bar omega times L plus 1. And that whole thing, AL dagger AL, is equal to HL minus E0L. And from that, I can extract what the E0L is. So the principal quantum number that we're using here, we're denoting 0 because that state using a subsidiary condition that AL acting on psi 0L is equal to 0, we immediately know that the energy of that state is E0L. And when we combine those constants together, we find E0L is H bar omega times L plus 3/2. So from this, we have actually now found the ground state of every Hamiltonian HL. You see, it's really quite beautiful. With this, we have found the ground state of every one of the problems we were trying to solve, rather than starting from one and working it out. And again, this is a little bit different than the way that we work with it with a chain. So in order to get the wave functions or the eigenfunctions themselves, we're going to have to use the intertwining relationship. And this is the shortcut that we're going to use to find now all of the energy eigenstates for every angular momentum all at once. So how do we do that? Well, first we got to work out what that intertwining relationship is. You have to remember that when we work with the factorization chain, we look at AL dagger plus E0L, and we normally would call that HL plus 1 auxiliary. But what we're going to do is we're going to actually try to see how does that relate to the HLs. So what I'm going to do is I'm going to remember that AL dagger AL plus E0L, that's equal to HL. And so this term on the left-hand side is actually equal to HL plus the commutator of AL with AL dagger. Now I can substitute in and calculate what that commutator is. And that commutator, when we plug that in, I'm plugging in what the HL is. That's the P. That should be a PR squared. PR squared over 2m plus H bar squared L times L plus 1 over 2m R squared plus 1/2 m omega squared R squared plus 2 commutator of PR with the minus I H bar L plus 1 over R plus I m omega R hat. That's the superpotential that we are taking the commutator with. The factor of 2 comes from the fact that I have 2 cross terms. They come in with opposite signs, but they also come in with opposite orders, which is why we get the factor of 2 in front of that commutator. Okay, now we can evaluate that commutator again. Commutator of PR with 1 over R is equal to IH bar over R squared. Commutator of PR with R hat is equal to minus IH bar, just the constant. So we substitute that in. And you see here now what we get is one of the terms is H bar squared L plus 1 over M R squared. There's no 2 in that denominator. So when I combine that with the term H bar squared L times L plus 1, it's like I'm adding a 2 to the L in that expression. So it's going to become L plus 2 times L plus 1. And I'm going to have a H bar omega that is left over. So that is now the expression of HL plus 1, because I will take the value of L times L plus 1. If I increase L by 1, that becomes L plus 1 times L plus 2, which is what we have there. So I can replace that by HL plus 1, and then there's an extra constant left over, an H bar omega. Now, I just want to really be careful here to make sure that this is not our auxiliary Hamiltonian. We're relating these expressions that normally form the factorization chain into these other Hamiltonians that we need to work with and find their eigenvalues as well. So it is very similar to what we do when we find the auxiliary Hamiltonians, but because we can relate it to this other Hamiltonian, we find that it has this extra shift of the H bar omega. And what that tells you is that the auxiliary Hamiltonians are actually related to the HL Hamiltonians by a constant shift proportional to H bar omega. So we're going to now use this relationship in our intertwining relationship. We're going to calculate what happens when I take an AL dagger and I move it past an HL. So let's substitute in what the HL is. That's AL dagger AL plus E0L. Let us now put everything inside the parenthesis. And now let's focus on that AL dagger term. If you look above, you can see I can rewrite that in terms of HL plus 1 plus H bar omega minus E0L. And so I'm going to do that. And now I'm going to pull an AL dagger factor out to the left. And you see that there's a cancellation of a minus E0L and a plus E0L. And I'm left just with that H bar omega. And this is our intertwining relationship. What it says is that when I move an AL dagger through an HL, it increases the index of the HL by 1, and it shifts the energy by H bar omega. And again, this is slightly different from what would happen with an auxiliary Hamiltonian, but just bear with me. This slight modification is what we need in order to get all of the energy eigenfunctions all at once. All right, so as I've mentioned before, another way of thinking about this is that the auxiliary Hamiltonian corresponding to this situation is that HL plus 1 plus H bar omega. All right, on to the energy eigenstate. We're essentially going to guess what the energy eigenstate is and then prove that it is correct. And we look carefully and work carefully with that intertwining relationship in order to do that. We see that it involves a shifting of the H and a shifting of the energy. So if you recall that the ground state for each HL satisfies this subsidiary condition, AL psi 0L is equal to 0, we're going to use these results along with intertwining to come up with an ansatz for the energy eigenstate of the Hamiltonians HL minus M. And we're going to just take the string of these AL daggers, starting from AL dagger L minus 1 on the right and going all the way out to AL dagger L minus M on the left. The claim is if I operate with an HL minus M on that state, it's an energy eigenstate. So to verify that, we're going to just plug that in and see what happens. Now, what is the thinking that went into this guess if you wanted to work this out for yourself? Well, you see what's going to happen is every time, if I start with an HL minus M, I can move that Hamiltonian through all the way to the state, but each time I move it through, its index increases by 1. And I'm going to end at the end with an HL acting on that psi 0L plus some constant shift. And of course, that's going to be an eigenstate because the HL acting on the psi 0L gives me E0L times the psi 0L because it's the ground state of that Hamiltonian. So that motivates why we came up with this guess. And of course, I've also preempted and told you exactly what's going to happen with this derivation, but let's carefully go through it anyway. So we start by acting that HL minus M onto this state, and we're going to verify that the energy is E0L plus M H bar omega. So let's act that on that state. Let's focus on the first two terms. We can use intertwining to shift the order. That shifts the Hamiltonian by increasing its index by 1 and shifting the energy by H bar omega. Now we recognize that this is primed for another use of the intertwining relationship, so I can move it through and then I can repeat that. And in the end, so then I shift the index by another 1 and I shift the energy by another H bar omega, and then I keep repeating that until I get all the way to the end where I have an HL plus an M H bar omega. That acts on the state psi 0L, but of course psi 0L is an eigenstate of HL. Its energy is E0L, so I can replace it there. And then that's a number. I can pull that out in the front, and you see we now have an eigenvalue-eigenvector relationship. Okay, so this stops at the point where M equals L because there is no operator that exists for HL minus 1. And let me verify for you that that's the case. You see here, if I plug in L equals minus 1 into that lowering operator, I no longer have the divergence at R equals 0, which I must have in order to guarantee that I have a domain that goes from 0 to infinity for the radial position operator. And because that divergence disappears when L equals minus 1, it is no longer valid. So I can only do these chains all the way down to M equals L. And after that, I cannot go any further. All right, let's take a look at what these energy eigenstates are. I've actually written out for you what those energy eigenstates are using that formula that the energy eigenstate is equal to E0L plus M H bar omega. You get these different energy levels, and I've used these different colored rectangles to separate out the different angular momenta. Here I'm showing L equals 0, L equals 1, L equals 2, L equals 3. Let's plug in what these different Hamiltonians are. These are the HLs, not the auxiliary Hamiltonians. And I see that I have a slight error there. Those E2s, E3s, and E4s should be E02s, E03s, E04s. Sorry about that. And the states that we have are, of course, the psi 00, the psi 01, the psi 02, the psi 03, the psi 04. How we get the excited states, we operate on these with the corresponding A daggers with the index that is L minus 1. And that actually shifts us diagonally because the energy increases by H bar omega when we do this. And so we get this diagonal shift when we do that. And then we can repeat it again and we'll get the next diagonal shift as well. And these are the energy eigenstates. Now, you might be looking at this and saying, uh-oh, I'm kind of confused. This looks quite different from the way it looked when we were doing this with our auxiliary Hamiltonians. When we did a shift, we went horizontally in energy. Remember, the auxiliary Hamiltonians are exactly these HLs plus H bar omega. So you can see if I add in an H bar omega, let's look at the L equals 1. If I add in an H bar omega and call that an auxiliary Hamiltonian, you would see then that that would correspond when I added an A dagger 0 onto it to that horizontal shift in energy that you're used to. But then I would have to actually solve this auxiliary problem for each L, and that gets a little bit tedious. So instead, we're going to do it in this slightly different way, and you do have to kind of remember that this is a slightly different way that we're doing this. But it then allows us to solve every problem all at once. Now, if you really are struggling with this and you want to go back to doing it the standard way as a cookbook, you can do that. And I encourage you to then, pause the video and carefully go through that and do that. You'll get exactly the same energies and exactly the same states as what we have labeled here. Now, this degeneracy pattern is an interesting degeneracy pattern. So this is just summarizing what I have said, that this does not look like this normal factorization because the auxiliary Hamiltonians are shifted upwards by multiples of h bar omega, which would make everything then correspond to applying the A daggers moving horizontally in energy. But then those auxiliary Hamiltonians are not the physical Hamiltonians that we want the energy eigenvalues for, okay? Which is of course something that we know happens. Now, this degeneracy pattern, I'm going to unclutter this diagram and show you the degeneracy pattern. This degeneracy pattern is not what we typically get when we do a factorization method. It is occurring because there is extra symmetry in the problem. Whenever you see degeneracy in energy eigenvalues, that almost certainly means that there is some hidden symmetry in the problem that you haven't seen. So when we look at the different angular momenta, you see even angular momenta have degeneracy across energies, and odd angular momentum have degeneracy across energies, but the even and odds do not. And you can see that the degeneracy then skips. It's either all even angular momentum eigenvalues or all odd angular momentum eigenvalues that have these degeneracies. You also can see that in a given angular momentum, the energy shift, the increase in energy from each state is 2 h bar omega, not h bar omega. And that is also coming from the symmetry. This pattern and the symmetry is actually the degeneracy pattern that happens from a hidden SU3 symmetry. Now, I don't have the time to carefully go through and discuss what the SU3 symmetry is, but we will have a homework problem that will discuss some of the issues relating to this SU3 symmetry. Okay. I want to end the lecture with talking a little bit about this degeneracy, because solving this problem in the central force potential has given us some extra insight into the problem. And I wanted to show you how that works if we think about looking back at how we solved the problem in the Cartesian way. In the Cartesian way, we found that the energies were h bar omega, nx plus ny plus nz plus 3/2 in the isotropic case. And we don't see any of this structure of this degeneracy pattern that we had here. We don't see that kind of structure present when we have this Cartesian formula. Now, of course, all of the energy levels that I get for the Cartesian case are exactly the ones that we saw graphically on this previous page. And even the degeneracy is the same, because of course it's the same solution, but I want to carefully show you how that works. So let's focus on the case that has an energy that is 7/2 h bar omega. Now that means nx plus ny plus nz is equal to 2. And it turns out there are 6 different ways that I can do that. I can pick 2, 0, 0, 0, 2, 0, 0, 0, 2, or I can pick 1, 1, 0, 1, 0, 1, or 0, 1, 1. There's 6 different ways of doing that. If I look at it instead in terms of angular momentum, there also had better be 6 different ways of doing that. And indeed there are. This corresponds to the case with L equals 2 and the case with L equals 0. L equals 2 has 2L plus 1 states. Those are the different M states that are degenerate. And 2L plus 1 for L equals 2 is equal to 5. So there are 5 degenerate states for L equals 2. And there's 1 degenerate state for L equals 0. So the total degeneracy is 5 plus 1, which is equal to 6. And so you can see that we actually get the same degeneracy. So I hope you have enjoyed learning about the isotropic simple harmonic oscillator treated in the central force problem fashion using factorization. We're going to be covering other central force problems, primarily the Coulomb problem for hydrogen is going to be the next one that we solve, and we're going to take a lot of time to go through that because there's a lot of interesting stuff to do within that realm. And that then ends lecture 7 of module 7.